record. Okay, thank you. All right, so I'm belaboring this a little bit, but it's important conceptually to sort of think about like the terms versus the partial sums. And the idea is that the sequence, I should write this here, like S by definition is the limit as k goes to infinity, S sub k, or you could, I could write that just by plugging these things in, like replacing S with what we have. A sub n is the limit as k goes to infinity of the sum n equals 1 to k. Right, in some ways, that's like what this, putting an infinity up here is kind of a strange thing to do. And that's kind of by definition. Anytime you use infinity, it really should be a limit of something in math. And so that's really what we're saying there. Okay. Now, and then the point I wanted to make here was that geometric series turn out to be nice in that we could actually find a formula for the kth partial sum. Like this turned out to be, like this was 3/4, which is 1 minus a quarter. This is 7/8, which is 1 minus an eighth. This is 15/16, which is 1 minus a 16th. You can think of this as 1 minus a half. And so in the case of geometric series, we can actually find a formula for the kth partial sum. So we can actually evaluate the series and find its value. So for geometric series are very special. We can find an explicit formula for S sub k. Then take the limit to find the sum. So like an example, like e.g. for S is the sum of the powers of a half. We can see just by looking at it that Sk is 1 minus 1 over 2 to the k. Seems to be the pattern in yellow up there. Is that right? And then we took the limit, and so then S is 1 because the limit of this is k goes to infinity. This term goes away, right? So S is the limit as k goes to infinity of 1 minus 1 over 2 to the k, which is 1 minus 0, which is 1. By the way, there's a way to illustrate. I like to do this. Like an argument for y, a half plus a quarter plus an eighth plus a 16th plus a 32nd plus so on should equal 1. Like that infinite series should equal 1. Like in case you don't really believe it in your bones yet. You can actually demonstrate adding this series with a piece of paper. So here's a piece of paper. Let this be one unit. Let's do a half. Let's see if I can rip this without. Ooh, that's not too bad. So I want to do a half plus a quarter. So that's a half. Plus a quarter. Well, that's half of this, right? A half plus a quarter. That's a half plus a quarter now on the table. An eighth. This is a quarter, so half of this. An eighth. Half plus a quarter plus an eighth is on the table now. A 16th, that's half of this. You see where this is going? Like plus a 16th, plus a 32nd, plus a 64th, plus a 1 over 128, plus 1 over 256. It's a good representation of 1 over 256. 1 256 of a piece of paper. Plus 1 over 512. And so you can see, like, I'm always going to have stuff. I'm always going to have enough here to add to the pile if I do half each time. And eventually, I'm going to get rid of everything in my hand. And so the sum is going to go to 1. Partly it's just this pattern right here that we noticed, like if you write out the partial sums, there's a pattern. But actually in class Monday, what we did is we did the sort of general geometric series thing. And we actually could derive this more generally, like if we write out, I mean, okay, I'll put this down. But if we wrote out like S sub k is a half plus a quarter plus an eighth up to plus 1/2 to the k. And then we did the thing where we multiplied by a half. And that shifts over all the terms. And then if we subtract, that was this whole argument here, right? Like if we subtract, we get 1/2 S sub k equals a half minus a half to the k plus 1. And then if we divide through by a half, we actually get rid of a half in both of these terms. So that's the more formal argument of where that came from. But really, I was just noticing the pattern from the examples. But right, but I guess, so my point is, once we move past geometric series, life gets much harder because it's a lot harder to figure out. Most series are not this nice. Most infinite series are not this nice. So let me give you an example, which is a very famous example in math. Let's do the sum of the reciprocals of the squares. So this is 1 plus a quarter plus a 9th plus a 16th plus a 25th and so on. It turns out that this does converge. We'll give an argument for why that's true. But I'm going to actually go, I don't even really need the screen for this because I can't see the mouse. I'm going to ask Wolfram Alpha to sum the first 100 terms of this series, just to like get an estimate. That's funny. Okay, so give me a decimal. Okay, so it's about 1.635 or something like that. If you sum a bunch, if you just sum like a lot of terms. So mathematicians stare at this for a long time and were like, okay, that's kind of random. But somehow somebody noticed that there's actually an explicit formula for this. It's actually, anybody want to guess? Does this look familiar to anyone? Can you use some fundamental mathematical constants and come up with this? Is it pi over 2? Kind of close, but no. Yeah. The what equation? Oh, is it? Oh, the golden ratio. Oh, yeah, it actually does look kind of close to the golden ratio. Golden ratio is 1 plus root 5 over 2. That's, have people heard about the golden ratio? That's the most pleasing rectangle to the eye. Should be the rectangle that if you cut off a square, you get a rectangle with the similar proportions. And it turns out that like if this is 1, then this is that. That's the golden ratio. I think the golden ratio is about 1. What's the golden ratio? Anybody want to do that on their calculator? 1 plus root 5 over 2. I could ask. This is the golden ratio. It's a good guess. There are some of these constants that just, oh, it's 1.618. Okay, pretty close. But it's not the golden ratio. So mathematicians stare at something like this and like, they wonder, can we put this in terms of some fundamental constants, something to do with E or pi or the golden ratio, or there's natural log of 2 or something, you know, like, is there something going on? And it turns out there's an answer to this. And the answer is, I can't believe nobody guessed this. Pi squared over 6. it's amazing. It's kind of a crazy, it's crazy that this equals something that's nice. If you try pi squared over 6, you'll get about 1.61, 1.63, whatever it is. Actually, let me do that. Pi squared over 6 is it's 1.6449 actually. So I guess, because I didn't add enough terms, I only added 100 terms here, so it's gonna increase more from that, whatever I wrote. So this is kind of shocking. It's also kind of, but not completely beyond the scope of this course to even show this pi squared over 6. Actually, there's this great YouTube channel. So part of this is I'm just trying to give you culture. Like there's like this is something that's like part of mathematical culture. Like any person who considers them a true math nerd should know this fact. And there's been some videos. There's some of those YouTube channels. I know you all watch YouTube math channels, right? In your free time? Hell yeah. Anybody have a favorite? Did I just call your bluff? What's it called? Organic Chemistry Tutors? That's a math channel? Oh, okay. There's like there's Numberphile, there's Mathologer. This is my favorite channel, 3 Blue 1 Brown. This has like the most beautiful videos. Like this guy actually wrote a whole mathematical animation language in Python. So it's everything like beautifully animated. But there's actually, let me see if I can find. So it's actually kind of hard to justify this formula. And again, it's like not something we're gonna do in this class. But he gives a really nice argument. There is a really nice video, this video. I'll try to maybe link to it, but oh my God. Whoa. Oh my God, more these ads, and I can't find the mouse button to skip. Okay. Yeah, so he actually talks about, sorry, I need to figure out how I can change the volume. I'm sorry, I gotta stop, pause this. So this is a thing, I mean, it's a really nice video. Let me see if I can find the sound. Where's the sound? See, why don't I have control over the output? Do I not have, oh, well, there's volume mute. Why don't I have volume control here? Oh, I didn't share screen either, probably sorry for the Zoom. Sorry, let me share. Or am I sharing? Oh, no. Okay. So this is just, yeah, like this is a nice representation, by the way. I'm sorry, I'm really having issues controlling the volume. I don't know. I guess if I wanted to make it just come out of the speakers for a moment, I could. I still don't control it. Sorry. Well, it's got, yeah, see, it was an unsolved question about like knowing what this constant was. Posed in 1600s, solved in 1730s. So these are, I'm trying to make it clear, this is a hard question, right? Mathematicians, nobody can answer it. Somebody thought about it and nobody can answer for like 100 years. And then somebody discovered it was pi squared over 6. And I'll put a link to this, but it's this beautiful video involving like lanterns, and there's this beautiful argument about if you have an infinite line of lighthouses and like what's the total brightness and stuff. And there's something about the fact that the lighthouses or that lamp, like light, luminescence or whatever, it goes down by like 1 over the square of the size of the brightness of the light source as it goes away from you. Because if you think about a light source and it goes like, it's like this big, when it's twice as far away from you in your mind, and it's half as small, so it's a half by a half, it's a quarter. That makes it because it's a two-dimensional like light source. And so you can actually realize this sum somehow as this brightness of all these lighthouses, and then he gives some crazy argument to show that like you can actually arrange them in a circle and then do this insane thing, and it turns out to give you exactly the answer. So anyways, it's a great video. I recommend watching it. Like I said, I'll try to put a link to it. But my point of all this was that this is a hard question. Okay, so that's immediately like hard. And so clearly, if you could find a formula for the partial sum and then take the limit, you should be able to get this. But that's what it's actually impossible to find a nice, like nobody can find a nice formula. These are like open questions in math. Like, can you find a nice formula for the kth partial sum? I'll say even more. Another example. 1 over n cubed. That's 1 plus an 8th plus a 27th plus 64 plus 125, so on. Again, you could ask for the approximate. This is approximately something. If you add up a million terms, get a computer to add a million terms, you can do it, and you get something. But what does it equal in terms of like fundamental constants? Open question in math. Nobody knows. If you figure it out, tell me. We'll write a paper. We'll get famous in math. Let me know. But there's like literally nobody. Like, so immediately I can give you questions that are like open questions in math, just by thinking about some basic infinite series. So I'm trying to give you hopefully I'm giving you the impression that this becomes like geometric series are super nice and very special, and we can sum them and they're nice. And then as soon as you do anything else, it gets hard. So it's going to be like the thing we kind of thought about with improper integrals, which is we're just going to ask whether they converge or diverge. That's really what we're going to do. If it converges, like we're going to be able to justify that this converges and this converges. But we're not going to be able to justify that this equals pi squared over 6, and we're definitely not going to be able to justify what this equals because we don't have nobody knows what this equals. Okay. Fun? Are you feeling the thrill of being on the frontiers of mathematics? Yeah, I can feel the excitement. Okay. So let me just say that, let me just write what I just said, which is that we're going to focus on issues of convergence or divergence, not the actual sums. So if I ask you to actually find a sum of an infinite series, it's almost definitely going to be geometric. There's like a couple other special cases that you can also sum, but they're very specific. So that's the first thing to think about. If I ask you to find a sum of a series, it better be geometric, or else it's kind of hopeless. Well, we will see some special cases actually later at the very, like towards the end of the semester. Like another one, actually I just say like there are some that are nice, like 1 over n factorial from 0 to infinity. 0 factorial is 1, it's considered to be 1. So this is 1, 1 factorial is 1, so that's 1, plus a half, plus a 6. Remember factorial, like in factorial, like 3 factorial means 3 times 2 times 1. Have we talked about factorials this semester? I can't remember. You guys remember your factorials? N factorial means 1 times 2 times 3 times 4 up to n. You just multiply the first n numbers. So 1 times 2 times 3 is 6. 1 times 2 times 3 times 4 is 24. 1 times 2 times 3 times 4 times 5 is 120. These numbers grow quickly. If I ask a computer for the first 1,000 terms, it's going to turn out to give you about 2.71828. Does that look familiar to anyone? What number is that? It's E. So it turns out this equals E, which is kind of astonishing. I tell you, there's like these fundamental constants like pi and E and stuff, and it's like they kind of show up everywhere. It's kind of disturbing because we don't know that many interesting constants, and yet so they kind of, anything that has a numerical value almost has to be like involve this. So actually, this equals E, not factorial. Now that I've introduced factorials, I have to put all my exclamation points in parentheses when I'm excited about something, or else you're going to think I mean factorial, right? So we'll show this later. We'll show this later in the semester, not later today. But still, it's special. Most of the time, we can't sum series. Still, it's special. It is special. Very rare to be able to sum a series. Okay. So instead, like I said, instead, we'll just ask about convergence and divergence. We'll just ask about convergence versus divergence. Right, we already saw that a little bit with geometric series, and that we can sort of tell very quickly whether a geometric series converges or diverges based purely on the value of the R, the multiplying factor, right? Okay, so here's the first big example I want to talk about. Because I did these examples, but there's something even more simple, which is just 1 over n. This is sort of something that you might think about, okay, here's something we could try to add. 1 plus a half, plus a third, plus a quarter, plus a fifth, plus a sixth, and so on. This is a famous series. It's called the harmonic series. It's got a name. Oh, I meant to look up why it's called the harmonic series, because I used to know and then I seem to have forgotten. But maybe I'll try to remind myself, or you guys can Google it. So the question is, does this converge or diverge? We're adding a half, then a third, then a quarter, then a fifth, then a sixth, so on. I don't know. Does it feel? You have any feel for this at all? Probably not. What's happening to the individual terms of the series as n gets large? They're getting smaller and smaller. So you're adding less and less each time. So you might think that means that it actually converges to something because it's slowing down to a stop, maybe, because you're adding less and less each time. Well, I'm going to give you an argument that actually I can make this expression as big as I want it to be. If I wanted it to be bigger than like 55,000, I could do that. If I wanted it to be bigger than 83 million, I could do that. And that means it's going to diverge. So it actually turns out this diverges. Let me see if I can give you an argument why. So it's weird though, because the individual terms go to 0. Even though the individual terms go to 0. It's always weird when you're doing something infinite. I mean, if you think about it, it's like that question I asked on the test about like, if a function goes to 0, must its integral from 1 to infinity be converge? And the answer was no, because we saw the integral like because we had the p-test. Like sometimes it converged, sometimes it diverged. And it's going to be something very similar here. Here's argument. Let me give argument number 1. I'll give you 2 different arguments because I think the first argument's a little specific to this, but I think it's very concrete. And then the second one is going to be more the things that we can generalize. Okay, so in order to give this argument, I have to write a lot of terms of this series. So just bear with me or start writing a lot of terms of the series yourself. This is fun. I'm going to do a dot, dot, dot and jump to 1 over 32. Then I'm going to do a dot, dot, dot and jump to 1 over 64. Okay, that's a lot of terms. I did 1 through 17, and then I decided to skip a little bit. But every number, 1 over 173,432 will show up eventually in this, right? Okay. Let me think about this. This is 1, right? Not controversial. That equals 1. That equals a half. A third and a quarter are both at least a quarter, like they're both greater than or equal to a quarter. So this right here is greater than or equal to 1/2. Oops. You believe that? A third plus a quarter is bigger than a half? It's bigger than, it's really, well, it's, I don't know why I said greater than or equal to. It's greater than a quarter plus a quarter, which equals a half, right? Now look at the next 4 terms. Each one of these is bigger than or equal to 1/8. One fifth plus a sixth plus a seventh plus an eighth. They're all at least an eighth, so the whole thing adds up to bigger than what? A half. Now let me do 9 through 16. What are each of these greater than or equal to? Well, the whole thing's gonna add up to a half, but what is each individual term? The smallest one is this one, right? So each individual term is bigger than a 16th or equal to a 16th. So this is greater than a 16th plus a 16th plus a 16th plus a 16th plus a 16th. I'm trying to write the same number of 16ths as there are terms here. I'm saying this one is, I'm comparing this one to 1/9, this one to 1/10, this one to 1/11. Yeah, which is a half. Okay, what if I do 1/17 through 1/32? Each term is bigger than 1/32. How many terms are there from 17 to 32? 16 from 17 to 32. There's 16 terms. From 9 to 16, there were 8 terms. From 1 to 8, there's 8 terms. So from 9 to 16, there's also 8 terms, because 8 plus 8 is 16. From 1 to 16, there's 16 terms. So from 17 to 32, there's also 16 terms. So this is greater than 1 over 32 plus 1 over 32, 16 times, which is a half. And I can always kind of suck up more terms and do this. Like this one right here is greater than 32, 1 over 64ths. Right, there's 32 terms from 1 over 33 to 1 over 64. And so that's another half. So argument number 1 is called the build by halves argument. And so do you start to believe, like, now do you believe at least that this sum is bigger than, say, 4? Because that's 1 plus a half, that's 2 plus a half, that's 3 plus a half, that's 4. So even if I go up to 1 over 64, that's bigger than 4. But I can keep doing this. You do have to suck up more and more terms each time. Like next time I have to do 64 terms and then 128 terms. But I can keep doing that forever because infinity is big. Right? So we can make this bigger than a half. I mean, we could probably actually do something explicit and say, well, let's see, if we want to go up to, yeah, so the partial, I mean, we can think about the partial sums and we can be kind of explicit, but I do want to claim, I hope there's some intuition here that this is going to kind of get as big as we want. It's just going to keep growing forever by this argument. So if I want it to be bigger than 10, I just have to take enough halves make 10. If I want it to be bigger than 1,000,000, then I have to build enough halves for it to be bigger than 1,000,000, and so on. So I guess you could say something like the following. Yeah, sort of. Informally, we can make this arbitrarily big. This arbitrarily big by taking enough terms to create as many halves as we want. To build as many 1/2s as we like. So that's kind of the argument that this diverges. I could be a little more formal if I want to do by saying, I think you could say a little more formally, you could probably argue that, like here, S4, if I just do those first 4 terms, is greater than 1 plus a half plus a half, right? S8 is greater than 1 plus a half plus a half plus a half, which is 3 halves. S16 is greater than 1 plus a half plus a half plus a half plus a half, which is 4 halves. S32, I really like to beat a dead horse sometimes, don't I? And so there's 5 of these, and this is 2 to the 5th, and there's 5 halves here. This is 2 to the 4th, and there's 4 halves here. So I think you could sort of argue that S sub 2 to the k, if I took the k, like not the kth partial sum, but the 2 to the kth partial sum, if I basically add the series up to 1 over 2 to the k, that's greater than 1 plus k over 2, 1 plus k times a half. Right, I think that's kind of the general. If you wanted to try to write a pattern, write this as a pattern, I think that's seems to be what we're seeing. And this certainly goes to infinity as k goes to infinity, right? As k gets large. I mean, you might need, like, if I wanted this to be bigger than like 1,000, I need 2,000 halves. So I need 2 to the 2,000 terms. That's a lot. That's a lot of terms. You need 2 to the 2,000 terms to make this bigger than 1,000. I mean, it'll get there before that, but you're guaranteed to make it bigger than 1,000 by taking the first 2 to the 2,000 terms. This class is always kind of ridiculous because you say like such large numbers sometimes, but it's kind of the point of the class actually. So this goes to infinity as k goes to infinity. So S sub 2 to the k goes to infinity as k goes to infinity. So the infinite sum diverges. Okay, fair enough. That's the first argument. And I do like this argument. I mean, I hope it feels concrete. Does it feel concrete? Do you believe me that I can make this as big as I want? Or am I just doing mumbo jumbo on the board? Who votes mumbo jumbo? Who votes this is ridiculous? Like this is nonsense. Nobody? Everybody feels cool with this? Okay. We'll try. It's hard to make infinite series stuff concrete. This is like one of the best. So I'm going to give a second argument, but let's take a break for a few minutes. It's 12:30. 35 minutes left. 35 minutes left in class. You've been staring at me for 45 minutes or so. Let's take a break for like 5 minutes, and then I'll give you the second argument, which is the more generalizable argument. Very little of this can I actually test you on, which is fine. We're talking about math. Math is beautiful. This is more a culture of mathematics, things that you should know. If you want to consider yourself an educated human being. Gotta know math facts. Really good for cocktail parties. Yeah, really. Math cocktail parties. Okay. All right, take a minute. Stretch, breathe. I'm gonna drink some coffee. That'll help me. Anybody started working on the write-up yet? Remember, you can talk to each other. You can talk to me. I'll be in my office this afternoon, 2:30 to 4. Friday morning and afternoon, I'll be there. I'm gonna sit down. I'll bother Lexi. Sleeping. Wants to sleep. It's too cold. Wait, I forget. Are you from California? I'm from Washington State? Oh, okay. Although this past summer it was so hot in Washington, right? It was like newsworthily hot. It was like people were dying. Oh my God. Oh. that was sort of disturbing. Oh yeah. Oh no. Yeah. I'm sorry. Not feel better. But definitely get out of here. That's 1 + k times a half. Sorry. Yeah. No, that's a good. Yeah, I didn't write that very clearly. That's okay. We still got a minute or two. Yeah. No, you're good. You're right. Thank you. That just means I'm counting k halves here. Good. Inverse Pythagorean theorem. It's not like a rigorous argument, but it's a beautiful. Yeah, some of the videos do get really. Like, I wish there were more videos of just like really good videos of just like basic math things. Like, just for fun, a few months ago, I tried to make a video just explaining why the 0th power is 1 and why the negative first power is like 1/. And sure. Where's my channel? Content. Oops. Sorry, I'm loath to switch it to the other one because it's so loud. Oh wait, there's a volume control. I'm an idiot. I didn't notice this volume. I don't know if you guys do this during my videos. If you skip ahead, if you click ahead. I misspoke there. It's 4 copies of 5. I hate listening to my voice. Here's if this is a good argument. Compelling arguments. I'll share for the benefit of slow math. You ever seen like slow TV where they like put a camera on the front of a train? You just watch the entire train journey. This is like slow math. It's like very basic, very. Oh. What is it? Voice. All of this should be very non-controversial. Not really add, I should say multiply into 5. You see where this is going? Oh, that purple is hard to see. Okay, I guess. See where it's going? Oh my God. I'm just droning on and on. Sorry. I want to stop, but I don't know when to stop. What number do you need to put right there? 1. And then if you go to the negative first power, do you see why what's gonna be natural to put there? 1/5. So there you go. All right, you got it. Sorry, I can't listen to myself talk. And I don't know, you might just be like, why is King showing us this? What the hell, what are we doing? This isn't calculus. But does that argument make sense? And does it feel like natural and easy? Oh, good, thank you. Yeah, I like the idea of making things that seem like hard to people, like natural and easy. That's kind of my, would be my goal. If, like eventually things should just seem natural. But, all right. And I meant to make one about like the half power and stuff, because you can also see like, right, if you, okay. So if you keep playing this game where it's like the 4th power is, or let me just say like the 2nd power is 5 times 5, and the 1st power is 5, and the 0th power is 1, and you multiply by 5 to go up there. But if I want to skip, like if I want to like skip a couple steps, if I want to go from like the 1st power to the 3rd power, what do I multiply by? How do I go from the 1st power to the 3rd power of 5? You multiply by 2 5s, right? So you could think about putting 1/2 in here and 3/2 in here and stuff, and being like, well, to go from here to here, I would want to multiply by 5 to the 1/2. And then to go to here, I'd want to multiply by 5 to the 1/2 again. And so to go from 1 to 5, I need to multiply by 5 to the 1/2 twice. What number do you multiply by twice to do the same thing as multiplying by 5? Square root of 5. And that's why 5 to the 1/2 is square root. So it sort of is just, it makes, if you put everything in these sort of patterns, it makes everything sort of natural and expected. So anyways, this has nothing to do with what we were supposed to talk about just now, so sorry. Who's annoyed at me? Who's annoyed? Prof King, let's do calculus. Who's like, okay, that was fine, but let's go back to calculus. Okay. Yeah, I hate math facts. Like every math fact should come from somewhere. Like there should be some way to feel in your bones why. Feel it in your bones why it's true. Well, but these are proofs, but they're also like argument. They're like pattern matching and stuff, Like I've been trying to think a lot about why dividing by a number is the same as multiplying by 1 over that number. I feel like that's really hard to explain to people. Like why dividing by 3 and multiplying by 1/3 is the same, or why dividing by 1/3 is the same as multiplying by 3. That's like really hard to explain to people. And like we sort of learn these, we just learn these rules that we just apply. And there's something to be said for like beating something into your brain to where it becomes second nature. Like it's not every time you think about 5 to the 0, you shouldn't have to go through this argument in your head just to see why it's 1, But it's nice to know where it comes from. So there's a lot of stuff actually in like educational theory about like, just like drilling and the usefulness of drilling things over and over again versus the actual like conceptual understanding and exploration. And I think you sort of need a balance of both. But anyways, okay, so let's talk about, let me give this area argument just to sort of, this second argument for why the harmonic series diverges, which is the one that's much more connected to the calculus ideas we've been looking at this semester. So I think I had argument number 1. So here's argument number 2. Did I stop the share of the Zoom and stuff? So, okay. For why this thing diverges. And it's an area argument. I'm going to show you can represent this series as an area, and it's an area that's going to be we're going to be able to see as an infinite area. So here's how we do it. I'm going to actually plot. You know, we have sort of here like a sub n is 1 over n. Thinking about just the sequence of terms, right? Of the series. And we can actually plot these. Like if I want to sort of plot, you can. We actually saw this sum for sequences. I think I even gave you a homework problem that was like plotting sequences like this. So here I'm going to plot height 1. So that's I'm going to stretch the y-axis a little bit just to make this. And so there's height 1/2. So if I actually wanted to sort of plot this sequence of terms, I could plot it like this, right? And these are getting lower and lower, but they're not decreasing by as much each time. Is that fair? As like a representation of the sequence? That's height 1, this is height 1/2, this is height 1/3, and so on. So I guess we're plotting n comma 1 over n. I wanted to say it that way, right? Okay, now I can make rectangles out of this. So here's a rectangle. That's height 1, base 1, area 1. I can make a rectangle here, base 1, height 1/2, area 1/2. This is area 1/3. This is area 1/4. This is area 1/5. This is area 1/6, and et cetera, right? We can keep doing this. Does that make sense? So I can actually represent the harmonic series as the sum of all these areas. So the sum from 1 to infinity of 1 over n is the sum of all the areas of these rectangles. Areas of yellow rectangles. Okay, but another thing I can do is I can draw the curve through all these points. Right? And what function is this? If I'm plotting n comma 1 over n, I'm really plotting x comma 1 over x, right? So this is y equals 1 over x, is that curve. There's another area we can think about, which is the area under this curve, right? From 1 to infinity. So in fact, the area under y equals 1 over x from x equals 1 to infinity is the integral. It's an improper integral. And remember, we can, if you want to remember like the nice way to do this, we make this a limit. We actually do the integral, natural log of x from 1 to b, and that's actually equal to the limit. I mean, you know the answer to this. You know this is going to diverge. I'm just reminding you of why. Natural log of b, b goes to infinity, which is infinity. So that area is infinite, right? But what about the yellow areas? How does that compare to the area inside the yellow rectangles? How does that compare to the area under the curve? Bigger or smaller? It's bigger, right? You have these overlap, these are sticking up over the picture. So in fact, if we look at it this way, so this is bigger than the area under y equals 1 over x from x equals 1 to infinity. And so really what I'm saying is that the sum here is actually bigger than the integral. It's kind of funny how similar these look, right? Like one's a summation and one's an integral, but you can kind of compare them directly just by drawing this picture. And this diverges. This is infinity. So this must diverge too. So in some ways, this is an easier argument than the other one I gave, but it's certainly less concrete and more built on like big things we've already done in this course, which is improper integrals. Does that make sense? We can do this area comparison. Questions about that? So this is a series that diverges. Right. Even though the terms are going to 0, I mean, that's the thing to think about. Like the individual terms are going to 0, which means the sum feels like it should be slowing down, but it doesn't slow it down enough to stop. It's slowing down, but it's slowing down. It's like a car approaching a cliff and it's braking. And the question is whether it's going to brake enough to not go over the cliff or whether it's going to go. I feel like I used to make like a Thelma and Louise reference, but now that's a movie that's like 30 years old and nobody knows. At the end of the movie, they kind of drive out over a cliff. Anyways, I won't spoil what happens after they do that. But anyways, okay. So right, okay, so this diverges. And maybe what I'll say is like, we can actually get a p-test, a very similar p-test like we had for improper integrals by doing the same kind of arguments. Because what if we do the same thing for 1 over n squared? That was the one that I claimed equaled pi squared over 6, so it does converge. But can I give an argument that it converges? So can we do the same thing for the sum of 1 over n squared? And the answer is yes. We just have to think about it a little more carefully, or we have to sort of organize it a little differently to get something that we can believe is finite. Okay. So similar argument for the sum of 1 over n squared. And the answer is like sort of yes. But we do have to be careful because if we can draw almost the exact same picture. I mean, honestly, can you tell that's 1 over x versus 1 over x squared? You know, like I can draw the same picture. I can plot n comma 1 over n squared. So let me do 1 here. Now it's a quarter, which is down here, and a 1/9. So notice this does drop much more precipitously than 1 over n, which was kind of the whole point of why the area under 1 over x squared was finite, but the area under 1 over x was not finite, remember? And got to be a little careful. I want to draw the same picture, but could I make the same conclusion? We got to think about this for a minute. If I drew the exact same picture, let me pull this board down for a second. If I drew the exact same picture, I could put a squared here and a squared here, right? It'd just be the exact same argument. But what does this integral do if it's 1 over x squared? What's the p-test say? It converges, right? So this would be finite, and this would be bigger. Does that mean this is definitely finite? No, we don't know, right? It could be finite or infinite. It's bigger than something finite. It's not that helpful. So we actually want to put these rectangles underneath the graph. And it's not so bad. In fact, I just draw them differently. It's almost like a left versus a right Riemann sum. Right, if I draw them here instead, that has area 1, that has area 1/4. Right, so we're plotting n comma 1 over n squared instead. This has area 1/9, 1/16, and so on, right? But I'm doing it more as like a, I guess that's more like a left Riemann sum, and this is more like a right Riemann sum. And so on, right? Because now if we draw the graph, there's the graph of y equals 1 over x squared. And then we're going to compare to the area. Now we have to be a little careful because we can't do the integral from 0 to infinity, right? It's improper at 0. But it's going to not matter because if we just think about this area again, that area right there is finite, right? So the sort of purplish area here, that's the integral from 1 to infinity of 1 over x squared dx. I could do it all out again, but hopefully you've done it enough that you've seen that this will converge. I think this equals 1 or something, but this converges. And now the thing is we don't have that exact inequality that we had up there, where the sum is just greater than the integral, because we actually have, this starts at a quarter. Like if I forget about this box, then all these other boxes are underneath the curve, right? So what this says is that the sum, I mean, maybe I should just write it more explicitly, that a quarter plus a ninth plus a 16th plus a 25th and so on is less than the integral from 1 to infinity of 1 over x squared, which is less than infinity. So this is finite. This converges. So the sum from 2 to infinity of 1 over n squared converges. But what's the difference between the sum from 2 to infinity and the sum from 1 to infinity? Right? What's the difference? Sum from 2 to infinity starts with a quarter. Sum from 1 to infinity starts with just 1, right? And so that doesn't actually, like, if we want the sum to 1 from 1 to infinity, that's just one extra term. It's 1 plus a quarter plus a ninth plus a 16th plus so on, which is 1 plus the sum from 2 to infinity. Oops, forgot the 1 over n squared. Right, I'm basically saying like any finite number of terms to start with don't affect convergence and divergence. It's the thing I've already said, which is convergence, divergence always happens in the tail, right? It never happens in the first billion terms. It always happens in the tail. So this is finite. So the whole thing is finite. Okay, does that make sense? Like I said, so it's a slightly different argument, but you can just move the rectangles around and you're only really having to worry about finitely many rectangles maybe not being contained in the area that we're talking about. And that doesn't matter, then we can throw those away. Doesn't affect convergence. Questions about any of that? So let me just state the p-test because it's the same test. Because we could do the same argument. Like, what if I wanted to do 1 over n cubed? Well, I would just draw the exact same picture there with cubed, 1 over n cubed instead of 1 over x cubed. And it would be the exact argument. What if I wanted to do 1 over n to the 1/2, 1 over square root of n? Well, I could draw this picture, but with 1 over root x here. And that's a divergent improper integral. So this area would be bigger. Let me just write that down. So yeah, I'm just trying to give you an argument why we have a p-test that's exactly the same as the p-test for improper integrals. It's nice to have this. Yeah, I'll just state this and then we can call it a day. So, right, so the sum of 1 over n to the p equals 1 to infinity. For p less than or equal to 1, draw the same picture as for the harmonic series. Draw the exact same picture. You have an area, the area of the rectangles is bigger than the area under the curve, or the area under the curve diverges. So the summation diverges also. For p greater than 1, you draw the same picture as for 1 over n squared. Oh man. And that converges. So really what I'm just saying is like, we have the sort of exact same p-test as we had for improper integrals. But it's not as obvious because we have these like, there we could integrate something. We had something we could actually integrate. So we could actually sort of get at it directly. Here you have to compare areas to an improper integral area. So it converges for p greater than 1, and it diverges for p less than or equal to 1. Okay. So we have a p-test for this, just like we had for it. Again, this is one very narrow class of infinite series. We had geometric series, which we could do, which were very specific. This is also very specific. But at least we can compare to these improper integrals we looked at and get the same thing. Okey doke. Should we call it a day? Let's do it. Go get some lunch. All right. I said I'll be back in my office at 2:30 if you have questions and stuff. But especially if we want to talk about the test, the write-ups. Don't leave the write-ups to the last minute. It's going to take a while to write things nicely. Even if you have the weekend, you should still start sooner. I guess it's because I always give like a 72-hour, so it'll be Monday at 5 p.m. will be the last minute. Don't wait till Monday afternoon to start doing your write-up. Yeah, there's no points off. It says late on Gradescope just because it's a late period, but I'm not going to count that as late. I just want to give you guys some more time because I didn't get the feedback back until Sunday, and I didn't really post the, all the like guidelines and stuff till Sunday night. So I just want to give you enough time. But you should start as soon as possible.
Thank you.
Yeah, see you.